Poincaré meets, the title says, okay. Poincaré meets Hardy. Okay, so of course I will say what is the Poincaré and how it's related to the Hardy. Yeah, so the plan of the talk, first I will give you the overview about the Hardy and Poincaré inequality. Then I will say the main results in the first order case where the improved Hardy inequality on the L2 gap. Of course, I will what the meaning of a L2 gap, what is the, I will tell you. And then I will, the next part of the talk, I will move on to the higher order inequalities that is known as the Poincaré-Hardy-Rellich inequality. And also I will discuss something on the abstract Rellich inequality with some Bessel pair. Okay, let me start with the first one, the overview. Okay. So let us start with the classical Hardy inequality. So let us take in the simplest form, like Rn, Euclidean space. The gradient of u square is greater than or equal to n minus 2 whole square by 4 integration mod u square by mod x square. Why it's important? You can see because of this the singularity that as extends to the origin, 1 by mod x square is a singular function. It blows up, but it is a very nice. It can be bounded with a gradient. So it is a it's an u by mod x and L2 function for when you use in CC infinity of Rn, and it's bounded above by the gradient. Okay, so this is the simplest form of the classical Hardy inequality. So the next important point is what is this constant? Whenever we are dealing with some inequality, the most interesting part is, of course, the inequality is there, but the next question is what is the best constant, or in other words, what is the sharp constant? Okay, so this is known as the Hardy constant or the Hardy sharp constant. But what is that? Moreover, that this constant is the sharp. That means if you replace with other constant c, which is greater than n minus 2 whole square by 4, this inequality does not hold. Okay, so this is the best possible or the sharp constant. In the literature, it is also known as the Hardy constant. Okay, this is the sharp. Now the question is here, another thing is that n greater than or equal to 3. The question is why I don't take n greater than 2 or 1. The question is, this is a very important part. This is known as, because the operator in R2 is a critical operator. I will come to that, what is the meaning of a critical operator. So in dimension 2, there is no Hardy inequality. That means there is no inequality of such form that gradient of u square is greater than or equal to some potential Vx u, sorry, this mistake. So there will be no comma, Vx u square dx. If such inequality holds true in R2, then V has to be equal to identically 0. So there is no way that you can have a Hardy inequality in a full space in R2 when n equal to 2. So that is the reason we have always considered this case n greater than or equal to 3. So of course, this is related to the some spectral theory. Why I will come to that. Okay. Okay. Now, why is this inequality interesting? First of all, this is a single. So if you consider this operator P, this is a Schrodinger operator minus Laplacian minus n minus 2 by 4x square. This is automatic from the Hardy inequality. You get that this inequality, this operator is not negative. Okay. Next question: this type of operator is used to model many physical and physical contexts like molecular physics and quantum cosmology in modeling something, because this type of Schrodinger operator is very important. I don't know much about the physics, and from a mathematical point of view, this is very important operator because this is used as a perturbation type operator, that is minus Laplacian minus V. Let's say this is equal to V, and these V 1 by mod x square type, and these type of V is known as the large perturbation. This is a spectral theoretic term. It's called large perturbation. It's always interesting to see what is the spectrum of this operator, and whether the essential, what is the difference, what is the spectrum, what is the essential spectrum, what happens if we are, what is there in a gap between the spectrum and the essential spectrum. All those things comes in that theory. Okay, so this is one of the most important operator. And of course, this is a Schrodinger operator, and to study is spectral behavior. Okay. So this is this is maybe the reason it's very interesting, of course. So let's go. So let us directly go to the generalized Riemannian case. That means, so what I did is this is in Rn, Euclidean space. Okay, so gradient is greater than equal to. So the next very important question is whether such inequality holds true in a Riemannian manifold. That means a non-trivial geometry. In a non-trivial geometry, in the Jules Caron in 1997 proved that for n greater than equal to 3, such inequality holds true, that n minus 2 by 2 whole square integration mod u square by the distance. This is a distance function from the fixed pole. This x naught is a fixed pole. Okay. But which type of manifolds? The manifolds where this Laplacian of a distance function is greater than or equal to a constant time by the distance. So automatically you can see that if your manifold is Rn, then this is equal to n minus 1 by R. So automatically this inequality is satisfied. Another large class of manifold where this inequality is satisfied is the Hadamard manifold. That means, namely, a manifold which is a complete, simply connected, and everywhere non-positive sectional curvature. You can prove that for such a manifold, the Laplacian of the distance function is actually greater than or equal to some constant time by the distance. So Hadamard manifold admits in particular, all Hadamard manifolds admits a Hardy inequality. Okay. Of course, one can also I can give you another remark is that if you have working on a sphere, such inequality is not true. You just take any constant function. This is not, because constant function on a sphere is of course a CC infinity function, and this inequality fails. Okay. So whenever there is a Hadamard manifold, this admits a non-negative. Admits a Hardy inequality. Of course, you have to be careful. I can allow my curvature to be non-positive. That means zero curvature is also allowed. That means Rn is also included. Of course, you can see that for the Laplacian of a distance function is equal to n minus 1 by R in case of the Euclidean. Okay. So that's for the Hadamard manifold. Okay. So there is a Hardy inequality there in the Hadamard manifold. Okay. Next, with a little bit more assumption on the manifold, let us consider a Hadamard manifold. But instead of allowing the curvature to go to 0, let us allow it the sectional curvatures are bounded above by a strictly negative constant. That is, kx is less than or equal to minus c. So, and c I'm not allowing to go to 0. If the Hadamard manifold whose curvature is bounded above by a strictly negative constant, then there is another inequality, very important inequality. It's satisfied. There is called the L2 gap inequality, or a Poincaré type inequality. Okay, namely, there exists a positive lambda positive such that the gradient of u square greater than or equal to lambda times mod of u square. So this is called the Poincaré, the famous Poincaré inequality. Of course, you have to be careful that I have used that the curvature. I have allowed the curvature to be bounded above by a strictly negative constant. In particular, in Rn we don't have in the whole space Rn we don't have a Poincaré inequality. Then the lambda is 0 because the bottom of the spectrum for a Laplacian in Rn is 0. So such inequality does not hold true in Rn. It holds only on the manifold whose curvature is strictly less than by a negative constant. Okay, so Hadamard and manifold whose sectional, here you can allow up to 0, but for a Poincaré you allow you have to be the bounded above by a strictly negative constant. So let us take a particular example. So that is a hyperbolic space. That means whose sectional curvature are the constant -1 or -c. That's not a problem. You take -1. The manifold who's having a sectional curvature -1. That is a prototype example, which of course satisfies this one because this is a strictly negative constant. Also, it satisfies because it's a hyperbolic space. The Hadamard manifold is also having a Hardy inequality. So, in a prototype example, in the hyperbolic space, we have both these two type of inequality. That is the Poincaré inequality as well as the Hardy inequality. In fact, we can have a more in the real hyperbolic space. The Poincaré constant, you can explicitly compute the Poincaré constant. This is actually equal to n minus 1 whole square by 4. This is not just don't confuse with the best constant of the Hardy. Hardy is the n minus 2 whole square by 4. So this is n minus 1 whole square by 4. This is the bottom of the spectrum. So there is of course there is no eigenfunction. This is not a eigenvalue, but this is a generalized eigenvalue. Okay, and this is called of course the spectrum of the Laplacian in Hn is the lambda to infinity. It's a continuous spectrum, and the bottom is n minus 1 whole square by 4. That means in other words we have a Poincaré inequality with lambda n minus 1 whole square by 4. That is the best constant. Okay, so we have a Poincaré inequality in the Hn with a n minus 1 whole square by 4 to be the best constant. Okay. And of course, we also have.
Debdip, yes. Could you please go back to the previous slide? I think I missed
this one.
No, the where you define the infimum. Overall, those. Yeah.
This
So it's never achieved
no. It
for
is not
any on
H1
hyperbolic
function.
space.
No. So this is
Okay.
not an eigenvalue. Okay. So this is this is called generalized eigenvalue. Okay. This is not achieved.
Okay.
Okay. So this is called generalized eigenvalue. So this is not a true eigenvalue. This is a generalized eigenvalue. So this is the bottom of the spectrum. Okay. But for as simple in Rn also we don't have. So the bottom of the spectrum is 0 to infinity. The continuous spectrum 0 to infinity in Rn. But since we are in a negative curvature, we have a positive spectrum. That is there is a gap. That is called the L2 gap. Okay. So of course, non-achievement of this extremal of this inequality also suggests an improvement. Now I will show that how this Poincare inequality and Hardy inequality together plays a role in the study of analysis in the hyperbolic space. Of course, then we can do in a general any Catton-Hadamard manifold with some curvature assumptions. But for this talk, I will be concentrating only on the hyperbolic space. Okay. But all these results can be generalized to the Catton-Hadamard manifold with some curvature assumptions. Okay. So let me now discuss what is the improvement I am talking about. Okay. So the question is, okay, the question is, does there exist a V, a positive V, such that the following inequality holds true? So this is, if the right hand side is 0, then this is a Poincaré inequality. So Poincaré says that gradient of u square is greater than equal to n minus 1 whole square by 4 integration u square. Or in other words, this minus this is greater than equal to 0. This is the Poincaré says, and of course, Poincaré says and more, and this is the best constant. Okay. Now my question is, okay, so the inequality is a strict positive because there is no functions in h1 of hn where it is achieved. So the question is whether does there exist a potential v strictly positive such that we have a greater than equal to integration v u square. Okay, whether such v exists. Okay, so Poincaré says that this v is 0. That's it. So now I want to improve this Poincaré inequality with some potential v. Okay. Now, of course, you will see that, of course, I want this potential to behave like a Hardy weight. And of course, why this potential behaves like a Hardy weight, whether it is possible that the potential should behave like a Hardy weight, that is a different story. But at least first question is whether we could improve this inequality with some potential v. Okay. Suppose if such v exists, there might possible that there might be huge set of v satisfying this above inequality. Okay. With some positive v, v1, v2, v3, many. But then the natural question is, what should be the largest possible v? Okay, so that we cannot have any v tilde greater than v, such that this inequality holds true with v tilde. So we want to find the largest possible v, such that, of course, I will quantify what is the meaning of a largest possible. Okay, but the meaning is the largest somehow. Formally, you want to find some largest possible v, such that this inequality holds true with that v. Okay. So we want to improve this Poincaré inequality with some potential v. Okay. Now we will see that, of course, we want to improve it with a whether this v behaves like a Hardy potential or not. That is and whether if we improve with the Hardy potential, whether this type of weight functions is the optimal one or not. Okay. Okay. Now coming back to, let me digress it from this theory and let me discuss something on the criticality theory or a spectral theory. Okay. Then we'll see how it is this criticality theory is related to these improvements. Okay. So let's just consider any second order non-negative elliptic operator with real coefficient. Forget about Laplacian. You can take any general second order elliptic operator. Okay. Of course, in particular, you can take Laplacian. Okay, on a manifold M. We call a Hardy type inequality with a v positive if there is a p minus v is non-negative. We call a v a Hardy type. Don't say that this Hardy type is always 1 by r square. This is a general statement I am claiming. The Hardy type inequality with a positive v means the p minus v, as in the operator sense, p minus v is a non-negative. Namely, the quadratic form associated with p minus v, that is p uu is greater than equal to integration vu square. That is the quadratic form associated with the operator p minus v. Okay. When we call this v to be a critical, that means an optimal Hardy weight. So the definition is a non-negative operator p minus v is called a critical in M. That is, we call v is an optimal Hardy weight for the operator p if this inequality p minus v cannot be improved with some w which is greater than equal to v and w is not equal to v. So we call v to be an optimal Hardy weight. Okay, if there does not exist any W which is greater than equal to V and W is not equal to V. Such, that should be the obvious definition, right? That V we called is called a critical Hardy weight or an optimal Hardy weight, okay, for any operator P, okay? Now the next question is how to find this critical Hardy weight. Of course, there are many ways. There is now the question is, okay, just a minute. Okay, so this so that is the P minus. Then we call this V to be a critical Hardy weight. That means there does not exist any W such that this can be improvable. Okay. Okay. So the next thing is, I will say that a second order differential operator is said to be a subcritical. Here we call it critical. P minus V is critical. Here that means we cannot improve this inequality further. If that is, then this operator is called critical. And we call a differential operator is subcritical if it admits a positive minimal green function. If it admits a positive minimal green function, then we call the operator to be a subcritical operator. Example, you just take a Laplacian in Rn, n greater than equal to 3. What is the Green's function? The Green's function is sub-constant up to a constant x minus y to the power 2 minus n. This is a positive minimal green function. Just come to n equal to 2. In n equal to 2, what is the green function? Is a log of x minus y, which changes sign. So in dimension 2, the Laplacian is a critical operator. In dimension n greater than equal to 3, the Laplacian is a subcritical operator. That is the reason we do not have any Hardy inequality in case of Laplacian in R2. And that is the reason we call Laplacian in R2 is a critical operator. Okay. And but for Laplacian in Rn, for n greater than equal to 3, it's called a subcritical operator. Whenever there is a subcritical operator, we can talk about the Hardy weight. Okay, that means we want to find a weight V such that P minus V becomes critical. That means the P minus V does not admit the, and in other words, P minus V does not admit a positive minimal green function. Or in this, all definitions are equivalent. Equivalently, these inequality cannot be improvable. Okay. Okay. And this is for a subcritical case, they're all. Now the question is, so given any subcritical operator P, does there always exist a V such that P minus V becomes critical? So this is the next natural question we can ask. Given any subcritical operator, you take now Laplacian in Rn. I will come to that. Taking any subcritical operator means which admits a green function. Whether you can explicitly construct such a Hardy weight, and such that this P minus V now becomes critical. Or in other words, the inequality is not improvable. That is the best possible inequality we could have with V. Okay. Of course. So the question is, given a subcritical operator P, construct an optimal Hardy weight, namely the existence of V such that P minus V become critical in M. Can there be an explicit construction in terms of the Green's function? Recently, these questions are completely understood by it's a very important paper by Davier, Frass, and Pinchover in 2014. They completely deduced the construction of Hardy weight. Let P be any second order subcritical operator in M. Okay, whatever you take operator. Subcritical means there exists a green function, the definition. So let G be the minimal positive green function with a pole x naught, and let U be any positive solution of the equation PU equal to 0, satisfying this assumption. Then we can always construct a Hardy weight. What is that Hardy weight? The Hardy weight is W 1 by 4 gradient log G by U mod square. This is that means for any given operator P, given any second order elliptic operator P, there always exists, at least they have constructed explicitly one Hardy weight W, which is given by the in terms of the Green's function, and such that this P minus W become critical. That means this is the best possible W one could have. You cannot have an inequality. That means PUU is greater than equal to integration WU square in terms of the inequality. Okay, and that W is the best possible choice of W. And of course, this is they prove. So this is a very general result. Given any, yeah.
I have questions. Yes. Function you define it is in terms of P or standard Laplacian.
I cannot hear you. I cannot hear you.
The green, what is the definition of this Green's function? It is in terms of P, elliptic operator P, or the
Yes. It's a. Since I said that P is a second order subcritical operator, there always exists a green. This is an abstract result. There always exists a green function. Okay, this is the green function with respect to P. Of course.
what does minimal mean here?
Minimal positive means that if there is something, if there are any other functions which satisfy the Green's function, that P of u equal to delta, then this G is less than equal to all those u. Okay.
So basically, you can take the infimum and it satisfies.
Yes, some kind of. This is some kind of. Yes, this is the smallest. You consider the smallest possible.
Okay.
G which satisfy the Green. P of G is equal to delta x.
And if I'm not mistaken, this subcritical is the definition, no? So it's subcritical if such thing exists, right?
Always exists.
Okay.
Yeah, if P is subcritical. So this is a very general result that if P is a non-negative operator, so there are two possibilities. Either P is a critical or P is a subcritical. Okay. This can be proved by using maximum principle. So I'm not going into the construction. You can always some exhaustion principle. You take a compact bounded domain. Okay, so you exhaust the manifold, and for each compact domain you have a this is the compact domain. You have a Green's function. Okay, with u equal to 0 on the boundary. Now, as the exhaustion means you have a bigger set. The Green's using the Harnack principle, there is always a sequence of Green's function which is increasing. And so the two possibilities, since by Harnack there are two possibilities, either it goes to infinity or it goes to a positive means the solution, another Green's function G. So if it goes to infinity, we call the operator is critical. If it goes to some fixed G, positive G, finite, then we call it a subcritical. So this is the way we construct the Green's function for any subcritical operator in a manifold. Okay.
And here M is any manifold?
Yes. With just has the pole. Pole means at that point the exponential map is a global diffeomorphism. That okay? With a pole. Just
okay.
So in this way, in a very abstract way, you can always construct a optimal Hardy weight. Okay, just give an example. Now I give you an example, very simple example is that you take P to be a Laplacian in Rn. As I said, n greater than equal to 3, you know there is the Green's function. Gx0 is Cn mod x to the power 2 minus n. And of course, Laplacian of 1 equal to 0. So it satisfies this. Also, we know that more as x tends to infinity, Gx goes to 0. So this everything is satisfied. G by u equal to 0 is satisfied, right? G by u is equal to 0 as well. Now you compute just gradient, the derivative of log of G. U is 1. So if you compute, you will explicitly get the Hardy weight. So W is n minus 2 whole square by 4x square. This is whatever Hardy weight has been discussed for till now. All this is recovers from this Hardy weight. Everything is recovered from this Hardy weight. Whatever the discussion. This is a very general result. Given any subcritical operator, you could find a Hardy weight. Okay. So I just give one example in Rn. Okay. Of course, you cannot do for n equal to 2 because there is no Green's positive minimal Green function. Okay. Okay. Now let me come to what happens in the hyperbolic space. This is an interesting part because here it gives you a Hardy weight. It is not, you cannot classify all the Hardy weights. That's another important part. There is a given operator P, there is an optimal Hardy weight, but this does not guarantee that all the Hardy weight will be of this form. Okay. Now this will come into this negative in this manifold case. Okay. So Laplacian, you take now instead of you take P to be minus Laplacian of H. That is the Laplace Beltrami on the hyperbolic space. It is not very clear. You have a heat kernel estimates and everything. It is very easy. It is well known that it admits a minimal Green function, positive minimal Green function. So P is a subcritical operator. Now P is a subcritical operator, and we can add P1 equal to 0 here also. Now use this recipe. So P is your minus Laplacian of Hn. Okay, U is 1. So again we can check easily. It's not very difficult to check that. Again, the Green's function at G by the Green's function for the Hn also as x tends to infinity at the infinity of the hyperbolic space, it goes to 0. It can be also easily checked. So everything is there. So you can construct this gradient of log G. Now you compute it. Okay. But unfortunately, these Green's functions are given are getting from the heat kernel. If you integrate the heat kernel from 0 to 2, you get the Green's function. So in hyperbolic space, this Green's function is not explicitly given. Okay, there is a bound less than equal to C1 and greater than equal to C1. There is not explicitly given the Green's function. It is a bound. So it's a very nice, but it has a bound, upper bound and lower bound. Okay. So there is no way that you can explicitly compute. But we can construct this W, that gradient of log G by U. And if you compute, then there is a W, definitely there is a W, Hardy-Wett, which behaves like n minus 1 whole square by 4 plus exponential minus 2r as r tends to infinity. Near infinity, Pinchover's and the Davies-Frost Pinchover's Hardy-Wett behaves like n minus 1 whole square by 4 plus exponential to the power minus 2r as r tends to infinity. In other words, they have obtained and just use their recipe, we will have this type of inequality. Gradient of u square dv minus n minus 1 whole square by 4 integration mod of u square dv. Okay, so this is a Poincaré inequality, and there is a w tilde dvhn, and this w tilde is of course non-negative, but which of course I take this n minus 1 whole square in the left hand side, and this w tilde behaves like exponential to the power minus 2r as r tends to infinity. That much is there. That means we have, this is a simple result, that just using the Davies-Frost-Pinchover's result, we can improve this inequality with w tilde. But how the w tilde behave? W tilde behave e to the power minus 2r as r tends to infinity. That much we know. That means we have improved this. First question is settled, right? We have improved this Poincaré inequality with W. But this is straightforward. There is nothing to do. Just try to compute it, you will obtain this. Okay. Now the question is, can we have this W tilde W tilde exponent? It decays like exponential minus 2r. But we want this W tilde to decay as 1 by r square at r tends to infinity. That means we want something like a Hardy-Wett, the true Hardy-Wett 1 by r square near infinity. But by their result, we could only get the decay as exponential minus 2r. So these methods only give you, of course, these methods gives you the improvement of Poincaré, but this not, of course, I said there might be many W. So there is one, this is one W, but we want now to get a Hardy type potential. We want W tilde to be of this C by R square, and we want to find the sharp constant C. Okay, and of course all this, and so that this W tilde becomes P minus W tilde becomes critical. In other words, we want to improve this Poincaré inequality with respect to the Hardy inequality. We want this inequality, gradient of u square minus n minus 1 whole square integration mod u square d of dvhn is greater than equal to integration u square by r square dvhn. And of course, we want to find that C, the sharp constant C also. And also we want to see that whether this Hardy-Wett makes this inequality critical. Or in other words, we want to find a optimal Hardy-Wett, another Hardy-Wett. Of course, we have a optimal Hardy-Wett W tilde which behaves, but we want something of 1 by r square. And also we want that has to be a critical Hardy-Wett or an optimal Hardy-Wett. Okay, this we've answered. Of course, we cannot follow their method. We cannot follow their method because this method at most give you exponential minus 2r. Okay, so we prove that it's completely different method. We have to use some kind of ground state transformation on a super solution technique. We use some kind of super solution technique, the step 1, and then step 2, we have to use some spectral estimates to prove that this is the gradient of u square dvhn minus n minus 1 whole square by 4. This is the Poincaré. Poincaré is greater than equal to 1 by 4 integration u square by r square. This is the 1 by r square. This is the Hardy-Wett, and plus n minus 1 n minus 3 by 4 integration u square by sine hyperbolic square r. And this makes the inequality critical. That means the operator we obtain now minus hn minus n minus 1 whole square minus 1 by 4 r square minus n minus 1 n minus 3 by 4 1 by sine hyperbolic square r is critical. That means you will not able to find any positive, any W which is greater than these potential. And this makes the operator H critical. So this is the sharpest, and all these constants are sharp. In mind, of course, unless you prove an inequality, unless you prove something sharp constant, this is of not much use. So this n minus 1 whole square by 4, this is a Poincaré constant, this is sharp. 1 by 4, we have proved it is sharp. N minus 1, n minus 3 by 4, this constant is also sharp. So, and also this weight is a critical. That means you cannot add further term with this inequality. This is the best possible inequality we could have in the hyperbolic space. And that is why we call this when Poincaré meets Hardy, because this is a Poincaré, this is a Poincaré, and 1 by 4, 1 by r square. This is a Hardy term. This is a Hardy term. So we call this a Poincaré meets Hardy. Okay, so this is the best possible inequality we could have in the hyperbolic. Now the question is, can we do it any manifold with negatively curved manifold? Yes, we can do this. We have to use some kind of Yau's comparison principle. In some, of course, some other geometric technique is needed. We can do it. Since we have done for the hyperbolic space, we have to do some kind of comparison argument to prove for any manifold whose sectional curvature is less than equal to minus 1 or minus c, the curvature of the constant curvature, that's the hyperbolic space. We have such a inequality with all possible best constants. Okay, but I am not for this is a very technical result, so I'm not going into that. But the main idea is to prove for the hyperbolic space, and from there you could get using the Yau's technique, we can go to the any manifold with negative curvature. Okay. Okay, so this is the for the first order. Now I will move to the
So for any manifold, do you have precise these constants that?
Yes. No, this lambda always the infimum of lambda exists.
Okay.
Yeah, this lambda depends on the manifold. Of course, this is not n minus 1 whole square by 4, but of course there is an infimum that lambda exists.
That depends only on the dimension or curvature also.
Curvature also. That depends on that, and we can prove that term as the curvature goes to the constant minus c, we recover the hyperbolic one.
So it doesn't depend on the I mean curvature. Of course, curvature is negative, but can it be infinite? I mean, can sectional curvature
yes,
go
very
to
good. Yeah,
infinity?
we can allow up to minus. It can bound it below, go to minus infinity.
Okay, you only need an upper bound, negative
That's
upper
it.
bound.
Yeah. That is the beauty of this Yau's idea. Yau constructed this. The geometric construction is a beautiful construction of Yau. You can do it for any manifold with that idea. Yeah, that's the strong. Of course, this is due to Yau. Yeah, this is his idea. It's excellent that you can do this comparison and go to up to the curvature which go to minus infinity also. But of course, we have only an upper bound.
Okay, thanks. Yeah.
Okay. So this is the one, but for technicality, I'm not moving into that. Let us move to the higher order case. Okay. That means instead of gradient, can we have for the Laplacian, and the Laplacian gradient makes everything. There we don't have the spectral theory, that the criticality theory of Pinchover and all those of Barry-Simon and all those things. We cannot use their criticality theory arguments here, because first step we have to prove it. To show criticality, we have to heavily rely on the spectral theory. Okay, so but of course this inequality is proved using some ground state construction, that super solution technique. But to prove, the second step is to prove the criticality. For that we need some spectral estimates. Okay, so but these type of things are not there when we go to the higher order case. I will come to that. Okay, so we did for the bottom of the spectrum. Now the question we studied that for lambda, we have a spectral gap. So lambda equal to lambda 1 is when n minus 1 whole square by 4. So what happens? Can we have a family of optimal Hardy weights for 0 to this? So we can vary lambda from 0 to n minus 1 whole square by 4. Okay, we can vary. So in this paper, we proved only for this case, for lambda, when lambda is equal to lambda 1, for minus hn minus lambda 1, we proved. Okay. Now for lambda equal to the Hardy-Poincaré study. Now the question is, can we have for any lambda between 0 to n minus 1 whole square by 4? Okay. Of course, for that we need some kind of new kind of Liouville type estimates. We need which we proved with my former colleague Biswas and our hypothesis, and of course in particular case Pinchover also proved in 2007 that using that Liouville type estimates we could able to do for any, of course, that for any lambda between n minus 2, we cannot go up to 0. Okay, there is some technical reason we can't go up to 0. Okay, but we have a family of Hardy inequality for any lambda between n minus 2 to n minus 1 whole square by 4. Okay, and this has been studied with Berkio and Grillo and Pinchover. Of course, we have crucially this Liouville type estimates is needed. Of course, I said this is because we want to go into the higher order case, and for that we need this type of for any lambda type of argument is needed. Okay, so next I will move to the higher order case, or sometimes it is called Poincare-Hardy-Rellich inequality. Okay. Okay. So the question is, can we do it for the higher order case for any lambda from 0 to n minus 1 whole square by 4? And what type of operator we are now interested? This is called a Rellich operator, Laplacian square Hn plus lambda Laplacian of Hn, and lambda varies from 0 to the bottom of the n minus 1 whole square by 4. So of course, P lambda, you just use the quadratic form. What is the quadratic form of P lambda? P lambda UU will be Laplacian of U square minus lambda integration gradient of U square. Just integration by parts will give you the P lambda UU is integration Laplacian of U whole square minus lambda integration gradient of U square. Okay. So this is the, now we want to have this type of inequality. Can it be done for the Rellich operator? This type of operator. We want to go for a higher order derivative. Unfortunately, we do not have this criticality theory or this type of Liouville estimates for a higher order operator, because this is due to main fact is because we don't have the maximum principle. Okay. So the maximum principle is not there for the second order operator. So that is the main issue. We cannot do it with the criticality theory or the spectral or Liouville estimates. Okay. Now, so we have to study in a completely different way. Okay. So this Ghusub and Moradifim in 2011, they provided a very general framework to obtain a various Hardy type inequalities and their improvement on the Euclidean space via Bessel pair. What is a Bessel pair? Bessel pair is nothing. It's Bessel pair means it satisfies some differential equations. I will come to that. Okay. The notion of Bessel pair has recently been exploited to obtain this type of Hardy inequality on a complete Riemannian manifold by Flynn, Lamb, Liu, and Majumdar in 2021. First of all, let me say what is the Bessel pair. We say a pair V comma W is a C1 function is called a Bessel pair on 0 to R, or for R between 0 to infinity, if the simple ordinary differential equation is satisfied by the function V and W. Then we call this pair V and W is a Bessel pair. So what are the examples of Bessel pair? You just choose V to be R to the power n minus 1 and R to the power n minus 1 n minus 2 whole square by 4 1 by R square. This will satisfy this equation. And of course, as you see, this is an Hardy weight. Okay. So there is some relation with the Bessel pair. This is the idea. Of course, this is due to Ghusub and Moradifim. They first want to see that there is a relation between study of the Bessel equations to the study of Hardy inequality. Okay. Okay. And this is an example. So this type of idea has recently been exploited by Flynn, Lamb, Liu, and Majumdar and to prove a series of Hardy inequality which recovers all our inequality which we have obtained earlier. They have proved in very recently in 21. They have proved. Let me say they have proved a very beautiful inequality. Gradient of course MGB a complete n-dimensional Riemannian manifold, and R is less than the distance of the 0 to cut locus. Of course, cut locus for the Kattan-Hadamard manifold is infinity. So R can go up to infinity in Kattan-Hadamard manifold, and R to the power n minus 1 V, R to the power n minus 1 become is a Bessel pair. Then this abstract such inequality holds true. Now, in particular, they obtained for a particular choice of V and W, like this type of choices, we can recover. They recovered all the existence Hardy inequality using this abstract inequality. Using their abstract inequality, they have recovered all ours. Of course, includes our Poincaré, improved Hardy, everything they have obtained using this Bessel idea, the Bessel's equation on the Riemannian manifold. Okay. Now the idea is whether can we do it? Can we exploit this idea, this Bessel pair equations idea, to go for the higher order case? Using one of my PhD students and with Barkio, we studied this question with Barkio and Rai Chaudhary. We studied that whether can we have such type of abstract inequality using Bessel pair for the higher order case. That means using Laplacian and the gradient, because as we know, we cannot use this type of spectral this criticality theory of argument or a construction of a super solutions technique. So can we have such inequality using the Bessel pair for a higher order case? Unfortunately, we could able to prove that this type of abstract inequalities, this is a V, of course, V and W is the Bessel pair. This is a radial Laplacian. Of course, I'm not. This is a radial Laplacian. It's a even better inequality we obtain with this. So we can always prove that this is less than equal. This is less than equal to VR times mod of Laplacian H and U square. This type of estimate, this type of comparison is always there. In fact, this is even a better inequality we have proved with this. Even not equality, we have proved it is an equality. Even not inequality, we have proved an identity. We have proved a Bessel pair identity for the Rellich inequality. I will come. There is no Hardy or Rellich term, but particular choice of V and W, we will recover these Rellich type identities. Okay, and the idea is, of course, the ideas rest on this spherical harmonic techniques and the spectral analysis of Laplacian on a sphere. Okay, these type of course, the proof is very long, but you have to use this spherical harmonic techniques and a spectral analysis of Laplacian on Sn-1. If you combining these two ideas, we could prove this. We can prove this Rellich inequality. We call it abstract Rellich inequality because there is no Hardy. Now we have to choose a particular V and W to get a such a for this type of we want for particular choice of, and we want to recover all this type of inequality for Poincaré, higher order Poincaré and higher order Hardy. Okay. So, but the problem is if you choose any previous examples of a Bessel pair, we are not getting any new kind of the one we want, an improved Poincaré inequality or a improved Rellich inequality for any lambda. So we need to next step, we need to construct a new kind of Bessel pair. Okay. So new kind of Bessel pair we have to construct. That meaning we want to construct a VW such that VW satisfy this Bessel's equation. Okay. Okay. So whatever earlier literature V and W are there, if you can put it directly, you can put it in this abstract inequality, but we are not getting anything new. Whatever we are getting, this the known improved Rellich or improved only just Poincaré improvement with some without a best constant on all those things. But so in that case, we have to construct a new kind of Bessel pair for to get all those Poincaré inequality improved one. Okay. So it was coming from this type of function. You consider this function r to the power n minus 2 by 2 sine hyperbolic r by r n minus 1. So the idea why this type of functions comes into play, this sine hyperbolic r by r, this is very important function playing a very important role in a wave equation. If you study the wave equation on the hyperbolic space, this type of function is called a conjugation function. The idea is the people what they do, they turn the wave equation to the hyperbolic space to Rn with some, of course, not directly Rn, this is called conjugate. They conjugate to the Rn with such kind of function. And that is the main idea we got from there, that this might help us in proving a new kind of Bessel pair, because this is deals with something Laplacian of Hn, we have to come to the Laplacian of Rn. Okay, some kind with some thing plus some remainder term should be there. And these type of functions play a role in that wave functions theory. So we use that type of function and we construct a very nice Bessel pair, that r to the power n minus, so V is your r to the power n minus 1, and your W in the W is r to the power n minus 1 W. If you see what type of function this satisfies this type of function with W, lambda is given by this. If you see this inequality, this abstract inequality, this is a term which is a bad term, right? Minus of n minus 1 VR f prime r. This is a very bad term because something a negative term in the right hand side. Okay, so if you study this function, you will have said that plus a positive n minus 1 psi prime by psi lambda cot hyperbolic. This resembles this term, very much resembles this term. Okay, and you can see that with this type of function, if you compute this type of function, this term and this term cancels out. Okay, and we obtain a family of, it's a miracle that these terms and these terms cancels out, and this forms a family of Bessel pairs, and we obtain a inequality of Hardy-Rellich type. So we obtain Laplacian U square, that is our goal, that is the Rellich inequality, that instead of gradient we have a second order plus lambda gradient plus Hn square lambda. Of course, what is Hn and what is this term, I will come to that. Gradient of U square by R square, a gradient of u square by sine hyperbolic square, a gamma n lambda, h n lambda plus this. This is an equality. Of course, now here you can use the Hardy inequality in the gradient u square, and you obtain all the higher order and use the inductively in iterative way. You can obtain all the this lambda varies from 0 to n minus 1 whole square by 4. Okay, and you obtain when you apply the Poincare inequality for the gradient of u square is greater than equal to n minus lambda square, then you will get n minus 1 whole square by 4 into integration u square. So you require the Poincare. So if you apply the Hardy inequality in this term, you will recover the Rellich Hardy inequality, Rellich Poincare inequality. So this gives all family of Hardy, Rellich, everything is satisfied just with a single identity, and this is rest completely on the idea of Bessel pair. Okay, and we obtain all the series of inequality which we obtain for the first order case, which we can do it here also in the second order case as well. So, and of course, for the different lambda, we can get a different constant. And this is the best constant. Of course, this constant, these are the best constant. Okay, now the question is, can we, all these constant are the best constant, and or something is called jointly sharp. It's a technical term, don't go to that. But the question is, this cannot be done for the general any Katanaga manifold, because we are heavily relies on this abstract theorem is heavily relies on spherical harmonic techniques, okay, and the spectral analysis of Laplacian. So the problem for the any manifold now for a higher order case, we don't have a Yau's comparison result. We don't have we can't use this type of Yau's comparison result we can go from Laplacian to everywhere. The problem from a Laplacian of Hn to any Laplacian of a manifold whose curvature is less than equal to the curvature of Hn. Here is we have to compare for the bi-Laplacian, and there is no comparison. At least we don't know any comparison for the bi-Laplacian. So whether we could compare the bi-Laplacian on the hyperbolic space with a bi-Laplacian on any manifold whose curvature is less than equal to the hyperbolic space. So scalar curvature. So we don't know any such type of comparison whether exists or not. So, and also this type of spherical, of course, this is not there in the general manifold. So we don't know how to, of course, one very simple generalization can be there is something called spherical manifolds. That means whose any point the metric is given by dr square plus some psi r square d theta square. Okay, so this is the Gauss. So Gauss lemma gives you a polar coordinate very locally. So in a manifold which admits polar coordinates globally, we call as symmetric manifolds. Okay, or called model manifolds. For a model manifolds, we can easily get such type of inequality. But of course, model manifolds are very much similar to of Hn. This is just a one-step generalization. This is not a real generalization. So we don't know how to do it for as we did in the first order case. But we don't know how to do this type of inequality to generalize for any Riemannian manifold whose sectional curvature is less than equal to the hyperbolic one. So as of now, we don't know. Maybe we are trying with Rai Chaudhary and Barkio, but still we don't know. Okay, so that is all. Thank you for listening. Thank you.
Thank you, Debdip, for a wonderful talk. So are there any questions? Okay, there is a question in the chat. Okay. So maybe I'll read it for you by Professor Ajit Iqbal. So her question is that, do you use Y? Okay, I think, do you use, yeah, I think there is something wrong in what she's written. So maybe you can have a look, maybe perhaps that will be better.
Okay.
I think she means is that, yeah, in the chat, if you see down.
I see the chat. Just a minute.
Okay.
Just a minute. Maybe I stop sharing the screen. Chat. Yeah, do you have such inequality in Poincare-Hardy-Rellich theorem on perturbation relating bounded operator on Catter's book of Widman motivated? No. That is the Catter's-Rellich theorem we don't use. That is a different thing. Yeah.
So
we did not use this thing. Yeah.
Sorry, I think there are people in the audience who work on Heisenberg group. So, well, are there Hardy-Rellich inequalities known for the Heisenberg group, first of all?
Hardy is very well studied in the Heisenberg group.
Hardy-Rellich.
Rellich, I think I have seen one paper, but I'm not sure.
And also,
whenever this Rellich is very less studied, means because as we go on a higher order, things are complicated. The main problem is we don't get the best constant. That is the main problem. We don't get to compute the best constant is very difficult in this type of, because of this bilaplacian. So things get very complicated, and so that is I at least for me this is the main issue I face.
Like you were mentioning that you use spherical harmonics, and I think there is such technique in Heisenberg group also, known as bigraded spherical harmonics. But then finding the right sort of Bessel pair is...
Yeah. But maybe I don't know, maybe it can, I don't know much about the Heisenberg group. That is a problem. So I can check whether we can have something or not. Definitely I can check.
Yeah. And also, I just wanted to ask that when you said, so do you have any extremizers also for these inequalities?
So for a Hardy inequality, we have studied completely. So for lambda between 0 to n minus 2, there is a number n minus 2. It comes something between that number 0. Lambda varies from 0 to n minus 1 whole square by 4. At n minus 1 whole square by 4, there is no extrema. For 0 to n minus 2, there is a number n minus 2 comes. From between 0 to n minus 2, there is no extrema. But from n minus 2 to n minus 1 whole square open interval, there is extrema for the Hardy. So Hardy case is completely studied. In a different paper, we studied these extremal things. That is studied. But again, while Laplacian, we don't know.
And so when you said Poincaré meets Hardy in that inequality, you have some extremizers?
Yeah. So when it's at the Poincaré, we showed that there is no extrema.
Yes.
But as we just lambda is less than the Poincaré, we have extrema.
Okay. Yes. Okay. Yeah. Thank you. There is another question in the chat.
I cannot see.
So it's written lower order derivatives are bounded relative to higher order derivatives. So it's a question.
No. You cannot say something like that. No. Not some special case, something is there, but like there is something called Bochner technique or something. That is a very special case, some estimates with a higher order and lower order derivatives are there, but in general, we don't have any such thing. At least I don't.
Is there any fractional Poincare-Hardy inequality for hyperbolic spaces?
Fractional is very well studied, I think, nowadays. Though, but of course, fractional Poincaré is also that n minus 1 will be 2s by
4. Poincare-Hardy.
No, fractional Poincaré-Hardy is not there still.
Yeah,
that is not still there. So I don't know. But in fact, we are trying that, but we did not get the full result yet.
Okay.
So we are trying something, but it's very vague. Means we are not. So some near infinity we are getting some. Again, the problem is the Green's function for the fractional one is again it's bounded above, bounded below. It's not. We don't have an explicit one. So the thing is that if we go for the supper solution technique, we have to go directly supper solution. And to construct a supper solution for a fractional one, it's we don't know which should be the candidate. That is a problem, the fractional one for Poincaré-Hardy and all this. But as such, for a Hardy and all these things are well studied. Yes, nowadays.
So I just wanted to ask another thing regarding this Bessel pair. So, I mean, is there some sort of classification of what kind of functions form Bessel pair? Or I mean,
yeah. These are well known. This Bessel sequence, this V and W. If you can express the Bessel pair of type 1, type 2 are there. So these are well known.
Okay.
So
Yeah.
these are well known.
So, are there any more questions? So, yeah, if there are no more questions, let's thank the speaker. Thank you very much, and hope to see you in Mohali.
Yeah, sure.
Yeah, we would like to have you there sometime.
Thank you very much.
Okay, then I'll end the meeting.